This is my Precalculus course. Today we're going to learn the Binomial Theorem. If you haven't done the homework completely and correctly from the last class, do that homework before watching this video. The Binomial Theorem is very important in the history of mathematics. You're going to use this theorem in your first calculus course. Isaac Newton did a lot of work with the Binomial Theorem. And this is a topic that I would consider to be advanced mathematics. We're at a level where it took some of the greatest minds to figure out some of these concepts. Isaac Newton he is considered one of the greatest mathematicians of all time, and possibly the greatest scientist of all time, and it took him a while to figure this out. Before we learn the theorem, we're going to review some of the exponent rules. We don't have time to go over every rule. You should be pretty familiar with these 10 rules. We learned them in my intermediate algebra course, but we're going to review specifically Rule 3 and 5. And this may seem a little easy for some students who have done a lot of these types of problems, but we just need to make sure that we know how to do this before we learn the binomial theorem. So we're going to use rule number 3 first. So rule number 3 says that if you have a product raised to some power, then that expression is equal to the first number in the product raised to that power times the second number in the product raised to that same power. So 5 to the third power is 125, and then we have x cubed, and there you go. So this is the rule up here if you want to reference that. So let's try example 2. We have negative 6 to the second power times y to the second power is 36y to the second power. So those are some example problems for rule number 3. Again, you can reference the rule up here. Try example 3. When you come back, we'll do it together. Okay, we're back. So we have 2 to the 5th power times a to the 5th power. 2 to the 5th power is 32. And if you got that answer, excellent. Try example 4. When you come back, we'll do it together. All right, we're back. So we have negative 3 to the third power times b to the third power is negative 27b to the third power. If you got that right, excellent. So that's just a little bit of review on exponent rule number 3. Let's do some review on exponent rule number 5. So this rule says that if you have some power raised to another power, then we just multiply the exponents. So that would be x to the 3 times 2, which is x to the 6th. And down here we have a to the 24. You don't have to write the intermediate step if you really want to, so we just multiply the exponents. So again, we have the rule up here. Try example 7, and when you come back, we'll do it together. Okay, we're back. You should have y to the 20th. Try example 8. If you got 7 right, good job. When you come back, we'll do it together. Okay, we're back. So we get b to the 30th power if you got that right. Excellent. Okay, so now we're going to combine these two rules. We're going to need both exponent rules number 3 and number 5. So first we're going to, let's bring these rules down. So we have them right in front of us. First we're going to use exponent rule number 3 because we have a product raised to some power. It's a product because we have 2 times x to the 6th raised to the third power. So using rule number 3, we have 2 to the third power times x to the 6th to the third power. That's this rule here. So x would be this number and y would be this number. I know that's kind of confusing because we have two x's there. So now we're going to use rule number 5 here because we have a power raised to another power, so we have x to the 18th. So there you go. So let's try it again. We're going to start by using rule number 3. And we get 16a to the 4th. So there's a couple examples demonstrating problems where we had to use both rules 3 and 5. So try example 11. When you come back, we'll do it together. Okay, we're back. So we're going to use rule number 3. And we can use parentheses, I guess, if you really want to. We don't really need to on the first term. So we get 81 y to the 16th. We used rule number 5 here. So if you got that right, excellent. Try example 12. When you come back, we'll do it together. Okay, we're back. So we use rule number 3 first. And we get 100 b to the 6th using rule number 5 in the second step. So if you got that right, excellent. So we reviewed exponent rules 3 and 5. We also need to learn an alternate type of notation for NCR. We're going to use this alternate notation when we learn the binomial theorem. It's just going to make things easier for us. So remember, this symbol up here is the number of ways that you can pick r distinct things out of n distinct things. Or it's the number of groups of r distinct things that you can choose out of n distinct things. So we learned this notation over here, but we also learned this notation. We didn't really use this notation very much, but you may see that. Well, now we have to learn this vertical type of notation where n is on top of r and we have parentheses. And again, this is going to make it easier for us to use the binomial theorem, or to write the binomial theorem out. So now we have 3 types of notation for counting the number of groups of r distinct things that you can create from n distinct things. Now recall, if you want to actually calculate the value, you would need this expression here. But we learned in previous classes that generally you want to use a calculator for this type of stuff. So we're going to do some practice to show how to use that type of notation. But this is really just the same thing we've been doing. It's just 3C1. So we can go to the calculator. That's actually a pretty easy problem. How many ways can you choose one thing out of 3? Well, obviously that's just 3. We don't really need the calculator for that. Now, notice I said we're choosing one thing out of 3. It's beneficial at this point in your math education to use a different way of saying this expression. C can stand for choose because we're choosing a group of things. In this case, it's only one thing, but normally you're choosing a group of things out of n things. So because we're choosing, you can think of C as representing the word choose. It also can represent the word combination because we're counting groups of things. So a group is considered the same thing as a combination in math. But it's beneficial for us to pronounce this as 3 choose 1 at this point in your math education. So we're going to just describe that as 3 choose 1. And so let's try this next example. This is 5 choose 2. how many ways can we choose 2 distinct things out of 5 distinct things? Well, we need the calculator for that. So you want to go to your TI-84 Plus and press the 5 button, and then at the upper left, push the math button, and at the right, push the right arrow key until you get to PRB, then push the down arrow key until you get to NCR, and then press enter, and then press the 2 button, and then press enter again, and you have your answer. So you should have 10. Again, that's all review. Everything we just talked about with your calculator is review, so you should be fairly familiar with that from previous classes. So I want you to try example 15. Again, we could use this formula, but it's a lot easier to use our calculators. So use your calculator with example 15. When you come back, we'll do it together. Okay, we're back, so that's 7 choose 4, which is 35 if you use your calculator there. Again, in your calculator, you should see 7 NCR 4. One more time, I'm going to tell you how to do this. So press the 7 button, then push the math button at the upper left, go to PRB with the arrows at the right, go down to NCR, push enter, then press the 4 button, then press enter again. I know that's a lot to have to do, but that's the easiest way to calculate. So now try number 16, and when you come back, we'll do it together. All right, we're back, so that's going to be 6. If you got that right, good job. Okay, so at this point, we need to figure out how to calculate these expressions here when we're choosing 0 things from n distinct things. And the reason that we're going to use this these types of expressions where we have a 0 here is because it just makes it convenient for us to write this expression in our binomial theorem, and there's other reasons that we need to define these expressions where we have 0 as the bottom number there. But when we plug in 0 into this formula, because remember, this is how you actually calculate these values, something weird is going to happen. So let's use the formula n factorial over n minus r factorial times r factorial, which is 4 factorial over 4 minus 0 factorial times 0 factorial. So 4 minus 0 is just 4, so we have 4 factorial over 4 factorial. And these just divide out and become 1, but what is 0 factorial? We haven't talked about that yet. Well, 5 factorial, for example, is 5 times 4 times 3 times 2 times 1. We learned that in previous classes. If you forgot, remember that's all factorial means, is you're multiplying by each whole number as we descend. 3 factorial will be 3 times 3 times 2 times 1, and 1 factorial would just be 1. So this all makes sense. But 0 factorial, we would probably define that as 0, right? It makes sense to just make that 0. But mathematicians have decided to define that as 1, even though it doesn't make any sense to do that. There's no logic when it comes to the math to define 0 factorial as 1. The reason mathematicians have done it is because they want us to be able to define these expressions so that we can use them with the binomial theorem. If 0 factorial is 0, then this expression would be undefined, because this blue 0 factorial would be 0. And remember, when 0 is in the denominator of a fraction, it makes the fraction undefined. So this whole expression would be undefined. So in order to make this expression defined, mathematicians have decided to make 0 factorial equal to 1. So that's a definition. Now, when mathematicians define something to be true, that means they just decide that it's true, and therefore it is true. So I want you to understand very clearly that there's no logic behind 0 factorial equaling 1. There's no mathematical reason for that to really be true. Mathematicians have just decided to make it equal to 1 so that we can use this expression in the binomial theorem, and there's other reasons also that you'll learn as you move through the math curriculum. So whenever you see 0 there, that expression is just going to be equal to 1. Now remember, we defined 4 over 0, or 4 on top of 0 with parentheses. We define that as 4C0. So conceptually what this means is we're choosing 0 things out of 4 total. So how many ways can you choose? This expression tells us how many ways you can choose 0 things out of 4 things, but that doesn't make sense. So you can see it doesn't make sense when it comes to the equation, and it doesn't make sense when it comes to the concept of counting how many ways you can choose r things out of n things. So this concept really doesn't make any sense. That shouldn't have any real value. So again, for convenience, mathematicians define it to be 1. So I'm not going to make you do these problems because it's pretty obvious what the answer is. They're all just equal to 1. All right, so we're going to use that in the rest of the class. So now we're ready to get to the binomial theorem. What exactly is the binomial theorem? The theorem tells us how to expand this expression. If we're going to raise a binomial, in this case a plus b, to some power, how do we expand it? Now, what do we mean by expand? Well, if we raise to the 0 power, we get 1. Anything raised to the 0 power is just 1. If we raise to the first power, we get a plus b, because anything raised to the first power is just whatever the number was to begin with. If we raise to the second power, we have to use FOIL, because that's a plus b times a plus b. So we have a times a is a squared, a times b is ab, b times a is ba, and b times b is b squared. Again, we're multiplying the first terms, outside terms, inside terms, and the last terms. We've done this thousands and thousands of times in my curriculum. So if you do that, you get this expression here, which simplifies to this trinomial if you combine like terms. Now let's try to expand a plus b cubed. Now we have a plus b times a plus b times a plus b. Now we can use FOIL here to get this expression like we did up here. And then we're going to have to multiply a squared times a, and then a squared times b, and we get these terms. And then we're going to multiply 2ab times a and 2ab times b, and we get these terms. And then b squared times a and b squared times b, and we get these terms. And then we combine like terms, and we have our expansion. So we learned how to do this type of math in my beginning algebra course. And that's what it means to expand these expressions. You're changing them into polynomials of this form. But as you can see, the math becomes very tedious. We don't want to have to do all this math in order to expand this expression to this blue expression down here. So the binomial theorem is an equation that helps us to go from here straight to here without having to do all this math. So we're going to talk a little bit about where the binomial theorem came from. We're not going to spend a lot of time talking about the derivation of the formula because most importantly you don't really need to know it. But another reason that we don't really want to spend a lot of time on it is because, like I said, it took some of the best minds in the world to figure this out. And although you're perfectly capable of understanding it once you know how to explain it, it does take some time to understand how this formula was derived. And because you're not really required to know the derivation of the formula, I'm not going to scare you by showing the derivation or spending a lot of time on it, but we are going to talk a little bit about where it came from. And if you want to spend some time on this, you can actually learn this yourself. So let's go ahead and expand as we did previously. So a plus b to the 0 power is 1. A plus b to the first power is a plus b. A plus b to the second power is this expression here. A plus b to the third power is this expression, and we keep going and going. And here's how the binomial theorem was developed. Mathematicians looked at this progression, and they started to notice patterns. Let's look at the bottom row here. Notice we have a to the fifth, a to the fourth, a to the third, a to the second, a, and no a. So that's useful information. That helps us to convert from this form to this form very quickly. We know that a is just starting at the fifth power and going down to the 0 power. This would be the 0 power if it doesn't show up. Now we can also see that b progresses. We have no b, and then 1b, and then b to the second power, and b to the third power, and b to the fourth, and b to the fifth. So it stops at the fifth power because that's what we're raising the binomial to. So b goes in the opposite direction. That's also very useful information. So we're starting to create a way to calculate these expressions quickly. So all of that is pretty easy. We learned how to deal with the a's and the b's. Here's where the difficult part comes. This is the part that took some of the greatest minds to figure out. Where do these yellow coefficients come from? You see, when we collect the inner terms, we perform FOIL, and we collect the inner terms, we get these numbers. In this case, it would be 2. In this case, we have 3 and 3. And of course, outside we have 1 there, so 1 coefficients. And we have 1, 4, 6, 4, and 1. So how do we know what those coefficients are going to be? Well, that is not as easy to figure out. That's why it took a lot of time for mathematicians to figure out this theorem. Now, mathematicians have come up with something called Pascal's triangle, which is all of the coefficients of this expansion progression. So you see that we have 6 here. That's the same 6 you have up there. These are just the same numbers that we're seeing in this expansion. So it looks like a triangle. And what some people like to do is they just memorize this triangle. The problem with that is that when you get down to these numbers, it becomes very difficult to memorize this triangle. And although we do see patterns with this triangle, some of the patterns are kind of tedious to have to remember. So we'd like to come up with an algorithm that helps us to find these numbers rather than just memorizing a triangle. So over time, mathematicians have figured out a way to actually calculate those coefficients. So again, figuring out A and B is not hard. It's the yellow coefficients that we need to figure out how to calculate. So again, we're not going to spend a lot of time on this, but let's use a plus b to the fourth power as an example. So we're going to take this expression over here, and we're going to rewrite it, a plus b to the fourth power. And of course that's a plus b times a plus b times a plus b times a plus b. And we're going to expand it out. And notice we wrote the expanded form here. But this doesn't look very familiar. That looks very strange. There's a lot of strange things going on. First of all, we didn't combine like terms. Remember when we used FOIL, we had some like terms and then we combined them to get 2ab. But what if we don't combine the like terms? What if we just leave them like this? Of course, that's a plus b to the second power. But what if we do the same thing for a plus b to the fourth power? Well, that's what we see here. Every term is written separately. We're not combining like terms in any way. Also, we're not using exponential notation. Instead of writing a to the fourth power, we're writing a times a times a. Instead of writing a cubed times b, we're writing a times a times a times b. Or a times a times b times a. Or a times b times a times a. Those are all a cubed times b terms. There's 4 of them. So why are we writing it like this? Well, the reason we wrote it out this way is because the number of blue terms is this number here. There's 4 blue terms. The number of purple terms is this number here. So we want to count the number of terms because that tells us what the coefficients are going to be. When we combine like terms, that's our coefficient. So that's why we wrote this expression in this way. And what you'll find out is the number of blue terms is equal to how many ways you can choose one thing out of 4 things. The number of purple terms is how many ways you can choose 2 distinct things out of 4 distinct things. Technically, they have to be distinct. And the number of yellow terms is the number of ways that you can choose 3 distinct things out of 4 distinct things. Now, one way to think about that is you're trying to figure out how many ways you can convert an A to a B. Well, you have 4 A's, right? If you look at this expression, you have 4 A's. You're going to convert one of them to a B. You can do it that way, or you can do it this way, or this way. Now, in counting, there's oftentimes a lot of different ways to think about counting problems, and this is a perfect example. That's the same thing as asking how many ways can you choose one thing out of 4 things? How many ways can you choose 2 things out of 4 things? And so that's how mathematicians figured out the binomial theorem. It actually turns out that the coefficients are calculated with these expressions by counting combinations or groups or choosing a certain number of things out of a larger group of things. Now, again, I want to make it very clear, it's not easy to understand why exactly that is. It took mathematicians a lot of time to figure this out. Again, Isaac Newton was one of the greatest minds in the world, and he spent a lot of time just trying to figure this out. So we're not going to talk about this any further, but when you multiply, every letter here is multiplied by every other letter, and that's why we have all of these options represented when we write these out. And so you can think about that if you want to. If you're interested in this, you can probably figure out why this works. But again, it's very important to understand that you don't really have to know any of this. You don't have to write any of this out. We're just talking about where this theorem came from. So if you write the general form of the binomial theorem, it looks like this. Now, I know that's very scary looking, but we have a to the n, and then the power goes down by 1, and then down by 1 again, and then we have a to the 0. The a just disappears. But b goes in the opposite direction. We start with b to the 0, and then b to the 1, b to the 2, and then the last b is going to be b to the n power, because n comes from here, right? But we have these expressions. That's what we just figured out how to calculate. We didn't really figure it out, but we talked about the basic idea. So this is the binomial theorem. And again, you don't have to know where it came from. I'm just giving you a kind of an idea of where it came from and how to figure it out if you want to explore that in more depth. Now, you may have noticed that this formula is pretty intimidating. In fact, the binomial theorem is one of the most complicated expressions that you're going to see. And a lot of students, when they look at this, their brains just kind of shut down. But in order to make this equation a little easier to look at, we're going to use a different type of notation for n choose r, and we talked about that earlier. This equation looks very complicated because of all these subscripts, but what if we could get rid of those subscripts and write those expressions in a different way? Well, we're going to do that. We talked about these 3 types of ways to notate combinatorics. So we're going to rewrite this equation that we see up here, but instead of using these blue expressions here, we're going to change them to these blue expressions down here. So we talked about that at the beginning of the class. So the binomial theorem is written in its typical way here. Again, we start with a to the n, and then we move down. The power moves down 1 and down 1 again, and then b goes up in power until we get to b to the n, and the coefficients are calculated with these expressions here. I know this is a very scary formula, but when you do practice problems, you're going to see that using the formula is really not that difficult. So I want you to get a picture of the binomial theorem, and we're going to do some practice problems. So we want to expand this expression. And we're going to have to write small because this is going to be a pretty big expression. So here's how we do it. We're going to start by writing x to the 6th, and then x to the 5th, and then x to the 4th, x to the 3rd, x squared, x, and then x to the 0. So we know that that's the progression for the x's. That's what the binomial theorem tells us.
Now, the reason that we started with x to the 6th is our binomial is raised to the 6th power.
We're then going to go in the opposite direction when it comes to the 2. So I'm going to use some different colors here. And for the 2, we're going to start at 0 power, 2 to the 0. And we have to write small so we can fit everything on the page. Then we're going to go to 2 to the 1st power, then 2 to the 2nd power, 2 to the 3rd power. Again, this is what the binomial theorem tells us, that we have this progression. 2 to the 4th power, 2 to the 3rd power, 2 to the 5th power, and then 2 to the 6th power. Notice we ended at 6. And with the x's, we started at 6. So it's important to space all this stuff out because we have more to write. Very important to write small when you are using these big powers here. 6 is a pretty big power to expand a binomial. And so now we're going to write the coefficients. So we're going to start with 6 choose 0. Now again, 6 choose 0 doesn't really mean anything. We have to define it as 1. Then we're going to go to 6 choose 1, 6 choose 2. I'm going to try to write as legibly as I can here, even though we're writing small. and then 6 choose 3, and you can see how this is progressing. 6 choose 4, 6 choose 5, and lastly 6 choose 6. Then we're going to write plus signs in between all these terms. And that is how we use the binomial theorem to expand this expression. Now, we have to simplify quite a bit here, so we're not done. But that's how we use the binomial theorem. Now, it's very important to understand that this expression here doesn't really have any logical interpretation. We just define it to be 1, as we talked about previously. And the reason that we want to write this expression in this way is it helps us to remember that we're just increasing the r value by 1 as we move along, and we start with 0. So it's just kind of a convenience to define that to be 1. That's one of the reasons that we define 0 factorial to be 1. So anything with a 0 under the n value, like I said, is 1. Now 2 to the 0 power is 1, and we're just going to keep simplifying here. And if we're going to choose one thing from 6 things, how many different ways can we do that? There's 6 different ways that we can choose one thing from 6 things. We don't really need the calculator for that. 2 to the first power is 2. And now we probably need to go to the calculator. How many ways can you choose 2 distinct things from 6 distinct things? And by the way, we don't care about permutations, right? We don't care about the order. That's why we're using 6 choose 2. That would be 6C2. So we want to go to the calculator for that. So you're going to press 6 in the calculator, and then you're going to push the math button and then right arrow key to PRB, and then down arrow key to NCR and press enter on NCR, and then press the 2 button and then press enter. And you should get 15. That value is 15. All right, so then we have x to the 4th. 2 to the 2nd power is 4. And now we have to go to the calculator again. And you're going to press the 6 button, press the math button, right arrow key to PRB, down arrow key to NCR, push enter on NCR, and then press the 2 button, and then press enter. And then press the 3 button, and then press enter. And you should get 20. So we have 20 x cubed, and then 2 to the 3rd power is 8. They're going to go to the calculator again and calculate 6 choose 4, and we find that that is going to be 15. And 2 to the 4th power is 16. And whenever you have an r value that is 1 less than the n value, it's just going to be equal to the n value. So that's just going to be 6. That's something useful to know for today's class. 2 to the 5th power is 32. And then how many ways can you choose 6 things out of 6 things? Well, obviously that's just 1, right? X to the 0 power is 1, and 2 to the 6th power is 64. So notice that we have to do a lot of simplifying. I'm going to write that x to the 0 power a little better there. And so now, let's simplify everything. We get x to the 6th plus 12 x to the 5th plus 60 x to the 4th plus 160 x cubed plus whatever 15 times 16 is. That would be 240. So we get 240 times x squared, and then we have to do 6 times 32. So that would be 192, and plus 64. So that is our final answer. So I know that that's kind of tedious to have to do all that. I started off with a big one. We had a 6 power expansion, but we were able to demonstrate how this works with all these terms. So you can see the progression. So if you want to expand x plus 2 to the 6th power, this is what it would actually look like. But if you tried to do it with the methods we learned in beginning algebra, that would take a long time. But with the binomial theorem, we can just write it all out and simplify, and then we're done. Now, again, I know that's a lot of work, but the good news is you're not really going to need to use this a lot in the math curriculum. It's just something that you're going to have to know for certain upper math concepts. And when you take a math analysis course like this one, a precalculus course, you're going to be expected to know how to use this formula. So let's try another one. This one's going to be a little easier because we have a 5 there instead of a 6. But this says y minus 3. So how do we do subtraction? Because our binomial theorem only deals with addition. A plus b raised to the n. A plus b. Well, this is y minus 3. So how do we do this? Well, we just rewrite it as y plus negative 3 to the 5th power. So it's going to work just like the previous problem. We'll start with the y's. So we have y to the 5th power.
And remember, the reason we start with y to the 5th power is y minus 3 is raised to the 5th power.
Y to the 4th power, to the 3rd power, 2nd power, y, and then y to the 0. I think I need to utilize a little more space there. And so now we're ready to move on to the negative 3. So now we're going to start with negative 3 to the 0 power and negative 3 to the 1st power, and we're actually moving up in power value. Negative 3 to the 4th power, and then negative 3 to the 5th power. Notice we end on 5 because that's the power, our expansion. So now we're going to write our coefficients. So we're going to start with 5 choose 0. Then we're going to move to 5 choose 1. Then 5 choose 2. Then 5 choose 3. Then 5 choose 4. Then 5 choose 5. And lastly, we're going to write addition symbols in between all these terms. Don't forget to write the addition symbols, or else your expression is not going to be correct. It's not going to make any mathematical sense. Okay, so now we're just going to simplify. If you're choosing 0 things out of 5 things, that's defined, the key word is defined to be 1. It doesn't make any mathematical sense. It's just defined to be 1. And of course, negative 3 to the 0 power is 1. How many ways can you choose one thing out of 5? Well, obviously that's 5. We don't need the calculator for that. Negative 3 to the 1st power is negative 3. And how many ways can you choose 2 distinct things out of 5 distinct things? Well, you want to go to the calculator for that. Again, press the 5 button, then the math button at the upper left, right arrow key to PRB, go down to NCR, press enter, and then press the 2 button, and then press enter. That's with a TI-84 Plus. If you're using a different calculator, you're going to have to look at the instruction manual. So that's going to be 10. Negative 3 to the second power is 9. And then we have to go to a calculator again. 5 choose 3. That's going to be 10 again. Negative 3 to the third power is negative 27. And again, whenever r is 1 less than n, it's just going to be n, whatever n is, that's 5. So 5y times negative 3 to the fourth power, which is positive 81. And how many ways can you choose 5 things out of 5 things? Well, obviously that's just 1. So y to the 0 power is 1. Negative 3 to the fifth power, that's going to be negative 243. So now we just have to simplify. So we get y to the fifth power minus 15 y to the fourth power plus 90 y to the third power minus 270 y squared plus 405 y minus 243. So that is the expansion using the binomial theorem. So again, I know that's tedious. I know that you probably don't want to have to do all that stuff, but the reason that we're doing this is to understand how the theorem works. Again, we're not really going to have to do this a lot in upper math courses. We just need to know how the theorem works because we're going to use the theorem when we tackle upper math courses. Okay, so let's try one more of these before you try one on your own. Okay, so let's try one more of these before you try one on your own. So we don't have to deal with the negative symbol on this problem. We're going to start with k to the third power because we have a third power expansion. And then k squared, and then k to the 0 power. And we probably don't need this much spacing, but I'm just being careful here. And we're making those red. Now let's go to the 4. We're going to start with 4 to the 0 power, and then 4 to the first power, and 4 to the second power, and 4 to the third power. Why are we ending at 3? Well, because that's the expansion. And why are we starting at 3 with k? Because that's the expansion. So now we write our coefficients. 3 always goes on the top. We always start with 0 as r. And then we go to 1. 3 choose 1. 3 choose 2. 3 choose 3. So, like I said, we probably don't need this much spacing in between, but generally you want to leave a lot of space in between if you can. So then we write plus signs, and that is the expansion. We just need to simplify. 3 choose 0 is defined to be 1. Remember, that's the definition. 4 to the 0 power is 1. And how many ways can you choose one thing out of 3 things? Well, obviously that's just 3. And 4 to the 1 power is 4. 3 choose 2. You can do that in your calculator if you want. That's going to be 3. So we have 3k times 16. And how many ways can you choose 3 things out of 3? Well, that's just 1. K to the 0 power is 1. And 4 to the third power is 64. So now We're going to write the final answer. We have k cubed plus 12k squared plus 48k plus 64. And that is the final answer. That's the expansion of k plus 4 to the third power. Okay, so now it's time for you to try. I'm going to leave problems 1 through 3 in the window. And I want you to try number 4. So write as small as you can and be sure to leave a lot of room. One of the most difficult things about these problems is just writing small enough to where you have enough room. So just be patient and see what you can do on number 4. And when you come back, we'll do it together. Okay, we're back. So if you got that answer, excellent. So that was kind of a big one. There was a lot of terms there. I want you to try number 5. This will be a lot easier because we have 1. 1's a lot easier to deal with. Also, it's only a 4th power rather than a 5th power. So try number 5, and when you come back, we'll do it together. Okay, we're back. So if you got that right, excellent. Okay, so on number 6, you have a t minus 4. So you're going to have to use problem number 2 to help you as a reference. Go and attempt number 6. Remember, you're going to have to write t minus 4 as t plus negative 4 so that we can use the binomial theorem in a way that we can understand. So try number 6, and when you come back, we'll do it together. All right, we're back. So that is the expansion. And even though that takes a lot of time, it takes a lot less time than having to actually use the concepts we learned in beginning algebra. So if you got that right, excellent. So now we're going to move to some problems that are a little different. They're the same types of problems, but a little different. So we have a subtraction symbol here, so we're going to have to change this to 2m plus negative 5p. All right, so now we're going to use the binomial theorem, but in this case, this is going to be the first number. That's going to be a, and this is going to be a over here, and this is going to be b. So this is going to be a little more complicated, but we can do it. So this is where our exponent rules come into play. So we have 2m to the 4th power. Why to the 4th power? Well, because that's where we're starting. That's the power of the expansion. 2m to the 3rd power, and then 2m to the 2nd power, and then 2m to the 1st power, and then 2m to the 0 power. Now we're going to deal with negative 5p. So we have negative 5p to the 0 power, negative 5p to the 1st power, negative 5p to the 2nd power, negative 5p to the 3rd power. And notice we're raising the whole purple expression to the power. We're not just raising p, we're raising the whole thing. So let me move this over a little bit. Then we have negative 5p to the 4th power. Okay, so now we have to write our coefficients. So we're going to start with 4, choose 0, y 4, because we have 4 up here. And then 4, choose 1, and 4, choose 2, 4, choose 3, and 4, choose 4. Now, 4, choose 0 is defined to be 1, right? Now, 2m to the 4th power, this is where we need to use exponent rule number 3. Remember, exponent rule number 3 says that if you have a product raised to some power, then that is equal to the first number in the product raised to that power times the second number in the product raised to that power. So that is going to be 16m to the 4th. So we're not going to write all that out because that would take forever to write it out. So I want you to do that in your head. And by the way, we forgot to write plus signs here. Sorry about that. Very easy to forget that. But again, if you don't write your plus signs, then the expression doesn't really have any meaning. How many ways can you choose one thing out of 4 things? That's 4. And 2m to the 3rd power, that's going to be 8m cubed. Negative 5p to the 1st power is just negative 5p. And how many ways can we choose 2 things out of 4 things? Well, that's just going to be 6. Again, you can go to your calculator to figure out what that is. 2m to the 2nd power, that's 4m squared. Negative 5p to the 2nd power, that's 25p squared. And how many ways can we choose 3 things out of 4 things? That's going to be 4. And 2m to the 1st power is 2m. And negative 5p to the 3rd power is negative 125p to the 3rd power. And how many ways can we choose 4 things out of 4 things? Well, that's obviously just 1. 2m to the 0 power is 1. And negative 5p to the 4th power is positive 625p to the 4th power. So now we just simplify. So we have 16m to the 4th power, and that's going to be actually negative 160m to the 3rd power. And we have a p, and 6 times 4 times 25, that's going to be 600 m squared p squared. And 4 times 2 times negative 125. You can use your calculator if you need to. We get 1,000, so that's negative 1,000 m p cubed, and then we have 625 p to the 4th power. So that is the expansion. You see that that's quite a bit different from the previous problems. It's a little more difficult. So I want you to try a problem like that. I'm going to give you an addition problem rather than a subtraction problem. So go ahead and try number 8. And when you come back, we'll do it together. Okay, we're back. So 3k is going to be, well, it's going to start with a 3rd power because we have a 3 here. And then we have 3k to the 2nd power, and then 3k to the 1st power, and then 3k to the 0 power. So we have plenty of room on this one. And now we're going to write 2l to the 0 power, and then 2l to the 1st power, so we're going up in power. 2L to the second power, and then 2L to the third power. Now let's write the coefficients. So we have 3, choose 0. 3, choose 1. 3, choose 2. And 3, choose 3. Okay. And now we can write addition signs in between all this. And how many ways can we choose 0 things out of 3? Well, that doesn't really make any sense, but again, it's defined to be 1. 3k to the third power, we just raise 3 to the third power and we get 27, and raise k to the third power. 2l to the 0 power is 1. And how many ways can we choose 1 thing out of 3 things? That's just going to be 3. 3k to the second power is 9k to the second power. 2l to the first power is 2l. And how many ways can we choose 2 things out of 3 things? That's going to be 3. 3k to the first power is 3k. 2l to the second power is 4l squared. And how many ways can we choose 3 things out of 3 things? It's going to be 1. And 3k to the 0 power is 1. And 2l to the third power is 8l cubed. So now we just have to simplify, and we get 27k cubed plus that's going to be 54k squared L, and then 36k L squared, and then 8L cubed. So if you got that right, excellent. Okay, so now we're going to go on to a slightly different type of problem, but we're still using the binomial theorem. The difference of this problem is that we have powers. So we have A and B. This is going to be A and this is going to be B, but both A and B have powers. So this is a problem where we're going to have to use both Rule 3 and Rule 5. Okay, so we're going to start with x squared, and that's going to be raised to the third power because we have a 3 here, and then x squared raised to the second power, x squared raised to the first power, and then x squared raised to the 0 power. So descending powers. And then we're going to start with 3y to the 4th raised to the 0 power, and 3y to the 4th raised to the first power, and then 3y to the 4th raised to the second power, 3y to the 4th raised to the third power. So notice the whole expression is being raised. You must use the binomial theorem correctly. So we're going to start with 3 choose 0, 3 choose 1, 3 choose 2, and 3 choose 3. Don't forget to write your addition symbol in between. And 3 choose 0 is defined to be 1. Very important to understand that that's a definition. It makes no logical sense mathematically. Now here's where we have to use rule number 5. You're raising a power to another power. So remember, you multiply the exponents, so we get x to the 6th. Anything raised to the 0 power is just 1. How many ways can you choose 1 thing out of 3 things? Well, obviously that's just 3, and x squared to the second power is x to the 4th. Again, multiply these exponents to get 4. Then 3y to the fourth raised to the 1 power is just 3y to the fourth. How many ways can you choose 2 things out of 3 things? Well, that's just going to be 3. X squared raised to the 1 power is just x squared. And here's where we have to use rule number 3 and rule number 5, the exponent rules. So we have a product raised to some power, which according to exponent rule number 3 is equal to the first number in the product raised to that power times the second number in the product raised to that power. Now we have to use rule number 5 to get y to the 8. We're multiplying these exponents. This is all stuff that you're going to be expected to know when you go into upper mathematics. Well, this is an upper math course, so you're really going to be expected to know this without anybody telling you. So that was the multiplier at the end there. Sorry, my computer's going kind of slow. So 9y to the 8th. And how many ways can you choose 3 things out of 3? That's 1. And then x squared raised to 0 is 1. And then 3y to the 4th raised to the 3 is 27. Y to the 12th. Again, you're going to use rule number 3 first, and then rule number 5 of the exponent rules to calculate that. Okay, so now we're ready to write the final answer. We have x to the 6th plus 9 x to the 4th y to the 4th plus 27 x squared y to the 8th plus 27 y to the 12th, and there you go. So for that problem, we had to use exponent rule 3 and exponent rule 5 at the same time in some of those problems, or some of those expressions. So I want you to use number 9 to help you do number 10. Now remember, you have a subtraction sign there, so you're going to have to rewrite this as 2a cubed plus negative b to the 6th raised to the 5th. And make sure you put the parentheses in the right place here, because if you don't, that's really going to mess things up. So go ahead and try number 10, and when you come back, we'll do it together. Okay, we're back. So we're going to start with 2a cubed. That's going to be raised to the 5th power. Why? Because we have 5th power. And then 2a cubed raised to the 4th. And then 2a cubed raised to the 3rd. I know this is tedious, but you have to do it. 2a cubed raised to the 2nd. And then 2a cubed raised to the 1st power. And let's shrink these a little bit and move them over. See if we can find enough room to write the last term. Again, that's one of the hardest parts of this type of math, is just finding room on the paper. Now we have 2a cubed to the 0 power. So let's double check, make sure we did everything correctly. There's a lot of numbers we're writing here. So now we're going to go to negative b to the 6th power, and we're going to raise that to the 0 power, and then we're going to raise it to the 1st power, and negative b to the 6th raised to the 2nd power, and negative b to the 6th raised to the 3rd power, and negative b to the 6th raised to the 4th power, and lastly negative b raised to the 6th to the 5th power. So now we're ready to write our coefficients, but I can tell I need to shrink this quite a bit. Okay, so we're starting with 5 choose 0. Why 5 choose 0? Because we have a 5 here, right? Then 5 choose 1, and then 5 choose 2, and 5 choose 3, 5 choose 4, and 5 choose 5. And now we're going to write plus signs in between. Again, I know this is very tedious to have to write all this stuff out. 5 choose 0 is defined to be 1. 2a cubed raised to the 5th power, that's going to be exponent rules number 3 and 5. So that's going to give us 32a to the 15th power. And if you want more practice with that, you can go to my intermediate algebra course where we have plenty of problems showing how to use those exponent rules. How many ways can you choose one thing out of 5 things? That's going to be 5. And 2a cubed to the 4th power is going to be 16, a to the 12th. And negative b to the 6th raised to the 1st power is negative b to the 6th. And how many ways can you choose 2 things out of 5 things? That's going to be 10. And 2a cubed to the 3rd power is 8, a to the 9th. And it's very important that you use the exponent rules properly here. We're raising a negative number to the 2nd power. That's going to be even, so it's going to be positive b to the 12th power. All right. But when we raise negative b to the 3rd power, it's going to be negative because we're raising a negative to an odd power. So now we're going to choose 3 things out of 5 things. And that's going to give us 10 again. And 2a cubed to the 2nd power is going to be 4, a to the 6th power. And negative b to the 6th raised to the 3rd power is going to give us negative b to the 18th power. And we can probably shrink some of this stuff. And how many ways can we choose 4 things out of 5? Well, that's just going to be 5. And then we have 2a cubed. And that's an even power, so it's going to be positive b to the 24. How many ways can we choose 5 things out of 5 things? That's obviously 1. And 2a cubed to the 0 power is 1. And we're raising to a odd power, so it's going to be negative b to the 30th power. So let's find some more room. And now we just have to simplify. So we have 32 a to the 15th power minus 80 a to the 12th power b to the 6th power plus 80 a to the 9th power b to the 12th power and minus 40 a to the 6th power b to the 18th power plus 10 a to the 3rd power b to the 24th power minus b to the 30th power. So that is the expansion. If you got that right, excellent.
Now, it's possible that you may see problems like this, where you're asked to find the coefficient of a term in a binomial power expansion. And in this case, they're naming the term by calling it the x to the 5th term. And there's 2 ways to do this. We can use a formula, or we can just write out some terms to get a feel for the term we need to analyze. And it's unlikely that you're going to be able to remember a formula relating to the binomial theorem or finding the term of in a binomial theorem, because we're not really going to use the binomial theorem that much in the upper math. So instead, we're just going to write out some terms, and that'll help us to review what we know about the binomial theorem. So I'm going to start writing out some terms. So we're going to start with 7 choose 0. Actually, let's start with x. So x to the 7th and x to the 6th and x to the 5th, and that's all we really need, because we're looking for the coefficient of the x to the 5th term, and a factor in the first term would be 7 choose 0, and then 7 choose 1, 7 choose 2, and we also have 3 to the 0 and 3 to the 1 and 3 to the 2 power, and then we're going to keep adding until we get to the last term, which is 7 choose 7, x to the 0 power, 3 to the 7th power. We don't really need to write all of this out. We're just doing this to help us answer this problem. So we're interested in this term here. And so let's analyze and find the coefficient. So 7 choose 2 is equal to 21. And 3 to the 2nd power is 9. 9 times 21 is 189. And so the coefficient of the x to the 5th term is 189. So there you go. So let's try another one of those. Now here we have subtraction, so before we do anything, I'm going to rewrite this expression as y plus negative k to the 5th raised to the 8. So it looks like it's going to be better for us to start at the right. So we're going to write the last term first. We're looking for the k to the 25th term, so we'll start with negative k to the 5th raised to the 8th power, and negative k to the 5th raised to the 7th, negative k to the 5th raised to the 6th, and here we have the one that we're looking for, negative k to the 5th raised to the 5th. So if we use exponent rule number 5, we're going to get k to the, or negative k to the 25th power. That's the term that we're interested in looking at. And so let's write our y's. We're going to have y to the 0, y to the first power, y to the 2nd power, and y to the 3rd power. And then we're going to have 8 choose 8 as a factor, and 8 choose 7. Now we don't really have to write all of this out, but we just want to make this expression available to you so you can see what's happening here. Then we have 8 choose 6, and then we have 8 choose 5. So we'll put plus signs in between, and a plus here with 3 dots, and then plus the first term. So we're going to have 8 choose 0, and then y to the 8th, and then negative k to the 5th raised to the 0. So we're just writing that so the expression is accurate. And like we said, we're interested in this term here because we're going to get k to the 25th. And let's double check all this stuff. Everything seems to be correct. Okay, so let's use the calculator to find 8 choose 5. That's going to be 56. And then negative k to the 5th power raised to the 5th power. Well, we're raising to an odd power, so that's going to be negative k. And then using exponent rule number 5, we get k to the 25th power, negative k to the 25th power. And then we get negative 56 y cubed k to the 25th. And then obviously the coefficient we're looking for is negative 56. So there you go, that's another one. All right. Go ahead and try 13. I want you to use number 11. You can take a picture of number 11 and take a picture of number 12 if you need to, or you can just keep it in the window. Try 13. When you come back, we'll do it together. Okay, we're back. 812. We're looking for the coefficient of that term. So if you got that one right, excellent. Okay, so let's go on to number 14. Try 14. When you come back, we'll do it together. Okay, we're back. So the coefficient of that term is obviously 4. So if you got that one right, excellent. Now we're going to do problems where we're going to not just find a coefficient of a term, we're going to find the whole term. It's looking for the second term here. And so let's write out some terms. We'll start with the first term. 6 choose 0 is going to be a factor. 6 choose 1 is a factor of the second term. And the last term is going to be 6 choose 6. So we're going to have x to the 6th, x to the 5th, and all the way down to x to the 0. And maybe we should change this expression just so we know how to use the binomial theorem. So x minus y to the 6th is the same thing as x plus negative y to the 6th. So we're going to have negative y to the 0 power and negative y to the first power, and then plus dot 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 all the way down to the last term, which is going to have negative y to the 6th power. So let's look over that, make sure we did everything correctly. Everything looks correct. So we're interested in the second term, which is going to be this term here. We want to figure out what that term is going to be. So how many ways can you choose one thing out of 6 things? Well, obviously that's 6. 6 ways. Negative y to the first power is negative y. So then we have negative 6 x to the 5th y. So that is the second term in the binomial power expansion. So again, we're finding the entire term, not just a coefficient of a term. So let's try one more of these before you try one on your own. Now we're finding the fifth term in the expansion of that binomial power expression. So there's going to be 10 terms in this binomial power expansion. That is the polynomial that results from expanding. So it looks like we're going to be right in the middle, so it really doesn't matter if we start from the right or the left. I'm just going to start from the right. So we're going to have 9 choose 0, 9 choose 1, 9 choose 2, 9 choose 3, and 9 choose 4. I think that's the term we're looking for. 1, 2, 3, 4, 5. And we're going to have 4k to the 7th raised to the 9th, 4k to the 7th raised to the 8th, 4k to the 7 raised to the 7th, 4k to the 7 raised to the 6th, and 4k to the 7th raised to the 5th. Again, it's not necessary for you to write out every single term. We're just doing this so we can understand the binomial theorem. So now we need L to the 0, L to the 1, L to the 2, L to the 3, L to the 4, and plus dot 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 plus 9 choose 9, 4k to the 7th raised to the 0 times L to the 9th power. So let's find a little more room. And we need plus signs in between. I'm going to use a different color for the plus sign so we can differentiate. And let's double check everything. So we're interested in this term here. We want to find that term. So let's calculate 9 choose 4 with our TI-84 pluses. 9 choose 4 is 126. So we have 126, and then 4k7 to the 5th power. That's going to use rule number 3, exponent rule number 3, and exponent rule number 5. 4 to the 5th power is 1024. And then we're going to have, so that was the third rule, and we're going to use the 5th rule to get k to the 35th power. Then we have L to the 4th. And we forgot a parenthesis. So then we're going to multiply, and we have 129,024. 129,024 k to the 35th power, L to the 4th. And so that is the term that we're looking for. That is the 5th term. So I want you to get pictures of number 15 and 16. Alright, so go ahead and try number 17, and when you come back, we'll do it together. Okay, we're back, so we're going to find the third term. So if you got that right, excellent. Go ahead and try number 18, and when you come back, we'll do it together. Okay, we're back, so we're looking for the last term. Answer, the last term is b to the 8th power. So if you got that right, excellent.
So that was the class today. If you'd like to take screenshots of all the work that we did to help you with your homework or to study for tests, go ahead and do that now. Here's screenshot number 1 and number 2 and number 3, number 4, number 5, 6, and 7, but don't go before you get your homework. Remember, the homework is not optional. It must be done completely incorrectly. Here's screenshot number 1 of the homework. And number 2. And it's not enough just to attempt the homework. It must be done correctly, so make sure that your answers are correct, and if they're not, go back and fix them. Homework that is incomplete or incorrect is not acceptable in any way, shape, or form, so make sure that the work is done perfectly. And I'll look forward to seeing you in the next class.